-1. Hi. Welcome back to Math 234. I'm still your host, Steve Dragoo. Today, we're reviewing for the exam, the first exam number 1. It's tomorrow, or if it's Thursday morning when you're watching this video, it's today. But for those of us currently in the classroom, our exam's tomorrow, Thursday, in recitation. Just go take it like normal, or go to your recitation like normal. You'll get the entire class period to take the exam. So it's 50 minutes long. And we have a practice exam that I think is fairly similar to the real exam, at least in length, style of question, all of that kind of stuff. And I think the questions are relatively similar. So of all of the options out there for reviewing for the real exam, I think this practice exam is the best option. So if you were going to spend your time focusing on only one thing to review before the exam, I would make it this thing. And without any further ado, let's start solving. So on the one side, I've got the practice exam as printed. You can find it you can find it right here in my notes. Just right click and download on that PDF in the upper left corner. And then I've also got the formula sheet that you're going to get on the exam. You do not need to print a formula sheet. We will provide it to you. And for exam number 1, we really only need the first page of the formula sheet. So it's the only one that I put in this document. You'll get both pages just in case you want it for some reason. But I think we'll only need page number 1. So that's all I put over here. So let's start looking for some solutions. We want to find the distance between the point 0, 1, -12 and the plane 2x, y, 2z, 2x plus y plus 2z equals 1. Cool. So what's our plan here? If I want to find the distance between a point and some plane, then my rough structure for how I'm going to go about doing that is I'm going to find any distance from this point to the plane. So any point that's in the plane, I'm just going to pick one. I'm going to look at a vector that connects my point to that point, and then I'm going to project that vector onto the normal vector. So I want to come over here and say that I will project onto the normal vector. And that normal vector is 2, 1, 2. That is my plan. That's, I think, the best way to find the distance between a point and a plane. So I can find any distance between my point and the plane just by picking some spot on the plane that I want to find the distance to. But if I want to find the shortest distance, or the most direct distance, I want to go straight at the plane, which will mean going along some vector that's parallel to the normal vector. So that's why we want to project onto it. And I am going to look over at the formula sheet and grab, no, try again. Vector projections right there. I'm going to grab the vector projection formula and project onto the normal vector. In particular, I'm going to be taking the magnitude of this normal, or of this projection vector, also known as the component or the scalar component, the scalar projection of my projection vector, which means I only need parts of this equation. And I'm only going to need u dot v over magnitude u. So I'll start just writing a few of those things down. Projection of v onto n is going to be v dot n over magnitude n times, or dotted with n over magnitude n. That's our full projection formula. But we only need the component of v in the direction of n which again would be the magnitude of that projection. Which is just going to be v dot n over magnitude n. Start splashing some color in here. So you can kind of see the different pieces that we're looking at. In particular, I'm going to just make my vector v turn blue. So I'm kind of paying attention to that vector as it goes through. All of the other vectors that are in there are just going to be the normal vector, the one that I already have, 2, 1, 2. So with that together, I need to figure out what my vector v ought to be. So I don't actually have it yet. Right? So in this particular case, v should just be any vector that connects my plane to the point that's given, so the point 0, 1, negative 12. So I need to find any point on my plane. So let's do that. Find any point on the plane. So a plane has an infinite number of points. In fact, it has infinity squared number of points because there are 2 different dimensions it exists in. So with this single equation where I've got 3 unknowns, an x, a y, and a z, I've got 2 free choices. So I get to just pick 2 things that I want to exist out of this point. So out of my x, y, and z, I get to pick 2 of them and just choose whatever I want them to be. So I'm going to let x and z equal 0. Now I should be able to find just one point where the x and the z values are 0, which ends up getting 0 plus y plus 0 equals 1. So I get the point 0, 1, 0 on my plane. That is just one of an infinite number of options for this problem to come up with just any point that's on the plane. So alternatively, I could have like 1, negative 1, 0 would also fit this plane. 0, 0, 1 half fits the plane. It does not matter what point you pick as long as it's on the plane. So again, there's a lot of variability in this problem. But now that I've got that, I can go figure out my vector v. It's gonna be my original point, 0, 1, negative 12, minus, and I suppose I should write it as a position vector instead of a point. So 0, 1, negative 12 minus that point that I just picked, which was 0, 1, 0 for my case, giving me 0, 0, negative 12. Anytime I want to find a vector that connects 2 points, I should just take the difference between them, or rather the difference between their position vectors gives me the vector that connects those 2 points. And we have a rather nice looking vector there. So now, to come get that distance, the distance, again, it's just the magnitude of that projection vector, or really the component of the scalar projection of that vector. So what do I need? The dot product of v with the normal vector. So that's 0 times 2 plus 0 times 1 plus 2 times negative 12 will be minus 24. All of that over the magnitude of my normal vector, which is going to be 4 plus 1 plus 4. Right? Square each element of the normal vector. 2, 1, 2. 4 plus 1 plus 4 is 9. The square root of that is 3, which will give me negative 24 over 3. And here's where we should add a little bit of extra to the part of the work that we've done so far. So I did leave off a small detail. And that is for finding the distance between a point and a plane, we don't care if that distance is positive or negative, right? When we're looking for the distance from a point to a plane, we're really looking for the absolute value, just the magnitude of that distance. So when I'm looking for the distance, I'm going to take the absolute value of my dot product. So negative 20, absolute value of negative 24 is just positive 24, and then 24 over 3 is 8. That's if I'm being the most correct. I would say that my distance is 8. I imagine that if you said the distance was negative 8, that doesn't feel like something we would penalize for on the exam. For this particular problem, I think a distance of 8 and a distance of negative 8 away both describe the same distance in terms of context. Again, to be most correct, it should be positive 8. But that's like a small little detail on this problem that I don't think is that significant. So I wouldn't sweat that too much. Either way, I got a distance of 8. If you've taken this practice exam already and you get a number different from what I get, do kindly let me know. It's entirely possible that I got the wrong one. Pretty sure that this is right. But again, if you got something different, let me know. We can figure out where we went wrong together. You know, just to make sure. So it would be nice to get all that stuff right today. Right, we got the distance between a point and a plane. Let's come look at another question. I want parametric equations of the curve of intersection between the surfaces, that paraboloid and that parabolic cylinder. So if I'm going to try to find a parametric set of equations for an intersection, we have two main paths that we go down for trying to find parametric equations. One of those is to try sine and cosine. I'm only really going to want to try sine and cosine if I think I've got something that looks circular. Maybe at first glance, we think that this thing kind of looks circular, right? Z is equal to 3y squared plus x squared. I see a y squared plus an x squared in there, so maybe that's circular. But really, to get the equation of a circle, I want square plus square equals a constant number. And here I've got x squared plus y squared equals z. So because I'm equal to a variable instead of a constant, I'm thinking probably not sine and cosine. Doesn't look enough like a circle for me to try sine and cosine first. So instead, we are going to try one of the three variables equal to t. So we're going to try x equal t, y equal t, or z equal t. And just see which one works. So might as well just start at the beginning with x equal t. If I get that, let me just say let x equal t, because it is a choice. But I've got to make one to get started. If x is t, that'll give me t equals y squared. To solve that thing for y, I would get the square root of t equals y. But really, if I'm going to go that route, if I'm going to try to take the square root of y squared, I need to end up with a plus or minus on the other side. And getting a plus or minus in my parameterization is not very ideal because that means I no longer have a function there, right? I don't get to express y as a function of t if I try this route. So I'm thinking right here, That's not a route I want to go. I don't think this is going to be a very good parameterization. So I'm going to say I don't think that method worked. And I'm going to try again. Maybe instead of that, I'm just going to draw a big strike through that whole set. Rather than trying to spend all that time erasing it. Just, strike through that, try something else. That parameterization didn't work. So I'm going to try another one. Instead of x equal t, I'm going to try y equal t because it's next down the list. So if I go that route, if y is equal to t, then I've got x equals t squared. And that's a function, right? X equals t squared is perfectly fine. I can plug that in. I've got now parametric equations for y and x. So as long as z works, then we'll be totally fine. Let's go take a look at what we've got. That means z equals 3y squared plus x squared. So this will be 3 times t squared, or 3 times t squared plus x squared, which is t squared squared, or t to the fourth power. Which is also a function. So at that point, I'm going to say that that's a good parameterization. I'm going to take that answer. So I won't even try z equals t. But I think if you did, you'd find pretty quickly it's not going to go so great either. So particularly with parameterizations, sometimes it's a bit of trial and error until you find one that works. Because there's a bit of an art to it. Things that I look for when I'm trying to come up with a parameterization that I think will be good for my first shot. I look for a relatively simple equation, right? Like x equals y squared is relatively simple, as opposed to the other one, which looks like there's a bit more going on. So I don't want to try that one right away. And then within my relatively simple equation, x equals y squared, I look for even powers. Because I don't want to try to unpack or undo an even power because I often don't get functions when I do that. So since y has an even power, I don't want to undo that. So I'm going to try y equals t as my first choice. If I were thinking about the problem before I just blindly tried one. So I'm going to go with y equals t. It was probably my best first choice. And as it turns out, it worked. Yeah. Right. Speaking of parameterizations, let's find parametric equations for the line of intersection between two planes. This is really just find the intersection between two planes, and then we're going to express that line parametrically. So lines, as we might recall, are a one-dimensional object, so I should only need one parameter to talk about them. And in fact, if I go over to my formula sheets, I can find an equation for a line. It's right here. Right. So an equation for a line, particularly one that's parallel to some vector v, is r of t equals r naught plus t times v. So I am going to use that in the problem we're about to do. That's kind of the thing I'm aiming at. And lines are really made up of two things. Even if you think all the way back to y equals mx plus b, you need two elements to figure out the equation of a line. I need a slope, which was m, and an intercept, b. Stepping that up to our three-dimensional, our Calc 3 definition for a line, I still need a slope and an intercept. But now my slope is some direction vector, v, and my intercept is just going to be some point that's on the line. Right? I don't need specifically an intercept. Y equals mx plus b has the intercept built in. But really, I just need any point to figure out that intercept value. So some r naught, some initial point for my line to begin at. So let's bring all that over here. We're going to have R of t equals R naught plus V times t. Those are the elements I need. So I need some point that is on both planes, and I need a direction vector. So let's start by talking about just the point that's on both planes. Why not? So I've effectively got a system of two equations that I need to solve for. And within that system of two equations, I have three variables. So my system is overdetermined. Does that mean no, it's underdetermined? I've got fewer equations than I do variables. So I have an underdetermined system. Either way, it means I've got a free choice. So free choice. And here's where I'm going to use the hint that was provided to me. There is a nice point of intersection on the xz plane. Right? The xz plane is the plane y equals 0. So I'm going to use that hint to kind of guide me toward finding a point that's going to work. So that's going to be my free choice because it came from the hint. I try y equals 0. I expect that I'll have an easier time solving those two equations. So I've got negative 2x plus 0 plus 5z equals 3. And I've got 4x plus 0 minus 3z equals 1. And what do we get here? I could do substitution to figure this stuff out. Or I could actually just try adding these two together linearly. If I just take 2 times that first equation and then add them down the line, what are we going to get? Well, I'll get negative 4x plus 4x is 0x. I'll get 10z minus 3z is 7z. And then 2 times 3 is 6, plus 1 is 7. So z equals 1. And if z equals 1, then what's x got to be? 4x minus 3 equals 1. So that must mean x is also 1. All right, so I can just verify that real quick in both plane equations. Negative 2 plus 5 is 3, and 4 minus 3 is 1. So I've got myself a point. 1, 0, 1. That'll be my R naught. So that's half the battle for coming up with the equation of this line. The other half is going to be finding the slope or finding the direction vector. And I need that direction vector to lie in both planes, right? Because this line needs to be in both planes. So my direction vector should be in both planes. Meaning that the dot product of v with either normal vector should be 0. So v dot n1 should be 0, and v dot n2 should be 0. Or in other words, my direction vector, my slope vector, needs to be perpendicular to both normal vectors. And if I need a vector that's perpendicular to two other vectors, I think the best way to find that vector is to take a cross product. So v, the vector that I want to find, it should be the cross product between my two normal vectors, which should look like the following. I, j, k goes across the top row. I'll put n1 across the next row. So how about negative 2, negative 3, 5? And 4, negative 2, 3. 4, -2, -3. Okay. So I'm going to come up with those normal vectors just to highlight where specifically I'm getting them from. So I think that's probably worth it. I am just reading the coefficients on x, y, and z within the equation of a plane to come up with its normal vector. Right, so I'm just getting those directly off of the equations that were given. I can also probably pop up to the formula sheet and see those things somewhere. Yep, so I've got cross products, which again will be helpful for us. It's right there. And also for a plane normal to some vector a, b, c, the normal vector just ends up being the coefficients on x, y, and z. So two things that I'm just grabbing off of the formula sheet. But all right, and how much space do I have before the next part? Ooh, nice, lots of space. So let's come try to calculate this here, or this here slope vector, the tangent, the direction vector. So I need a cross product of this thing. Let's try to get that. -3 times -3 is 9, minus -2 times 5 is -10. So I think that's negative, I think that's 9 plus 10, if I've done that right. Next up, my j component, I've got 5 times 4 is 20, minus 2 times 3 is 6, so 20 minus 6. Then for my z component, my k component, 2 times 2 is 4, or rather -2 times -2 is 4. Heard it both ways. Minus -3 times 4 is -12, so that becomes plus 12. All together, 19, 14, 16. And again, do you stop me if you got a different answer? You should figure that out. It'd be nice to, know it now before I've got to come back in 10 minutes to fix something. I'm pretty sure that's the direction vector that we should end up with. At least the last time I did this problem, those numbers sound familiar to me. So I just need to come back and express this thing as the equation of a line. So probably something like 1, 0, 1 plus 19, 14, 16 times t. Or if I wanted to express that all as a single vector, how about 19t plus 1, 14t plus 0, and 16t plus 1. Cool. So I think that's my vector, or that's my line, rather. Nope. Keep kind of highlighting where those t's go.
Is it fine on the test if we just leave it as you had it before on?
Yeah, so the question was, is it fine on the test if we just leave it right there? And yeah, that's totally fine. Although, what happened when I tried to circle that? Something weird went down. Okay, yeah. Yes, leaving your answer right here will be totally fine. Yeah. All right, some other stuff, even more parameterization. So consider a pair of curves, R1 and R2. One's given with parameter t, the other with parameter s. I want to find the point of intersection between those two curves. Step number one. So if I'm looking for the point of intersection between a couple of parametric functions, I'm given in each component function, right? So I know x equals something, then y equals something, then z equals something. And I want these two pieces to intersect, which means I should just set their component functions equal to each other. X of t should be equal to x of s, y of t equal to y of s, and z of t equal to z of s. So just right down the line, I'll set their components equal to each other, since that's what it ought to mean for two bits, two curves to intersect with each other. So on the one side, 5t minus 2t squared is equal to the other side, s squared plus 1. In the middle, 2t minus 1 is equal to 3s plus 6. And on the right side, 6 minus t, there we go, is equal to s plus 5. And I need to solve this system of equations. Once again, I've got a system of 3 equations with only 2 parameters. So again, I'm under, nope, this one's the other way around now, right? This one is overdetermined. Ugh. 3 equations with 2 unknowns means I've got an overdetermined system. I only really need 2 equations to solve for 2 parameters. So that's exactly what I'm going to do. So I'm going to just pick 2 of these equations and solve those 2 to figure out s and t. Because the system is overdetermined, it is entirely possible to find some ghost solutions here. Basically, I could solve for some s and t that will work for 2 of the equations, but then will not work once I try it in the 3rd equation. So on this question in particular, it's very important to check your work, right? So I need to find a solution and then check it against the 3rd equation that I haven't used yet to make sure that my solution actually fits. So with that said, I am going to solve. Come on, buddy. You're better than that. Sorry, hang on. My laptop is struggling pretty hard. No, not like that. Come. All I want to do is just highlight those 2 things. Yeah, there we go. And turn them green. And then highlight these 2 things. Turn them blue. So I'm going to work with these 2 equations because they look the easiest, right? 2 linear equations seem pretty simple. So I'm going to start by solving these 2 to figure out s and t. In particular, I'm going to get 1 minus t is equal to s. And then I'll substitute that into the other equation. This will become 2t minus 1 equals 3, and 1 minus t plus 6. Okay, I'm just going to substitute in right over there. And then it's just a matter of solving that equation. So let's see what it's there. 2t minus 1 is equal to 3 minus 3t plus 6. Group all my like terms. 5t. I'll have 2t plus 3t. On the other side, 3 plus 6 is 9. Add the 1 over to get 10. So t is 5. Nope. I'm not very good with numbers. T is 2. Right? 10 over 5 is definitely 2. Then once I've got that, I'll come back over to my first equation again. to say that 1 minus 2 is S. So S is -1. And now with those two together, I'll come check the other point or the other equation. So if I plug in 2 for T, this will be, let's try that back in black. This will be 5 times 2 minus 2 times 2 squared will be 4. I need to check if that's equal to -1 squared, which is just +1 plus 1. Let's see what we get. 10 minus 8 is 2 equals to 1 plus 1, which is also 2. Brilliant. That worked. Put a check mark right there. So I have a solution at t equals 2 and s equals -1. So then I just need to plug either one of those in. So R1 of 2 gets me a point somewhere. What are we going to get when we plug it in? It looks like 2, 3, 4. Right? I added all that stuff up, right? Alternatively, I could have done R2 of -1, and I better get the same thing. Again, I'll get 2, because -1 squared is 1, plus 1 is 2. -3 plus 6 is 3, and -1 plus 5 is 4. Cool, so that worked. Got the same thing for both, which is what we expected, right? We wanted these two curves to intersect, so they had better be at the same point. Then part number B. Find the angle at which these two curves intersect. And we're just going to express our solution in the form of arc cosine of something or arc sine of something, because I'm pretty sure it's not going to come out to a value we know from the unit circle. Bet that's why that hint is in here. Because again, all of this can be done without a calculator, is the idea, right? Because you won't have a calculator on the actual exams, the practice exam. We don't expect you to solve anything with a calculator either. Or rather, we expect you to be able to solve everything without a calculator, which means we've got to give you sort of exclusively nice to work with numbers. So that can be a decent hint on the exam. If you've got some numbers that are really not nice to work with, double check your method. So there might be an error in there. So if I want the angle of intersection between a pair of curves, what am I going to look for? If I've got two curves and I want to know what they look like near their intersection, I probably want to look at their tangent vectors at the point of intersection, right? Two curves are going to share an angle of intersection, the angle of intersection of their tangent vectors, meaning I better just go calculate those real quick. So I want R1 prime, right? We're going to see some calculus in this multivariable calculus exam. So R1 prime of T is going to be, I think that's 5 minus 4T. Let me zoom out so I can actually remember what they all are. 5 minus 4T, 2, and -1. I'll also go get R2 prime. This one will be of S. And it's equal to 2S, 3, 1. Right, and then from there, I need R1 prime of 2 So that's what I found my t-value was, the point of intersection. So that'll be, let's see, 5 minus 8 is -3 to -1. And I need R2 prime of -1, which looks like -2, 3, 1. Right, I've got my tangent vectors. How do I turn that into an angle? Well, again, we could pop over to our formula sheet and go see if it gave us some equation for an angle somewhere. Right, I'm hoping to find an angle between two vectors. And conveniently, I see that in the definition of the dot product. Two vectors, u and v, can be expressed in terms of an angle that's between them, and just those two vectors. So the dot product is equal to the product of their magnitudes and the cosine of theta, which means to get theta by itself, I'm going to want to solve for something like cosine theta is the dot product divided by the product of the magnitudes. So I want R1 prime of 2 dotted with R2 prime of -1 divided by the magnitude of R1 prime of 2 times the magnitude of R2 prime of -1. Notation ends up getting a bit fun, but we got it all in there. So let's go look at what those things are going to be. So straight line for my fraction bar. Let's see. -3 times -2 is 6. Plus 2 times 3 is also 6. Plus -1 times 1 is -1. Center that a little bit. Divided by a couple of magnitudes. One of those is the square root of 9 plus 4 plus 1. The other is the square root of 4 plus 9 plus 1. Both of those look to me like they're going to be the square root of 14. Square root of 14 times itself will be just 14. So in the end, I think I've got 11 for my numerator and 14 for my denominator. So to get just the angle theta, it should be the arc cosine of 11 over 14. Cool, that's my angle. One other thing that I meant to say earlier, but then I think I didn't. I was mentioning those ghost solutions, or those extraneous solutions. You got to be careful with those because I think if you tried doing this same process, get to the point where you got t equals 2, then if you try plugging that into the x equation, you'll end up getting something like s squared equals 1. And we have a bad habit of saying if s squared equals 1, well, then obviously s must be equal to 1, right? Because it looks like the best solution, 1 squared is 1. So yeah, sure. S squared equals 1. S equals 1 is a solid set. But you'll see that that's not the correct answer here, right? S was supposed to be -1. You'll find if you plug in 1 for s, you do not get 2, 3, 4. So be careful when you're checking these points here, when you're checking for a point of intersection. The correct solution to s squared equals 1 should be s equals plus or minus 1. And then you would really have 2 points of intersection that you need to check. So my backup point to that is stick with the simplest solution or the simplest equations for solving, and then just check those against the more complex one. All right, I don't really like having to unpack square exponents because we do end up getting those extraneous solutions often. So I chose specifically to focus on the two linear equations when solving my system. So just a heads up there. But all right, on to classifying surfaces. Quick note on the exam, or the exams in general. Our plan is to write all of the exams to be just free response questions. We think that they're generally the best type of question for Calc 3. So we in fact wrote an entirely free response question, including this one, and then decided, when we want you to classify surfaces, we should probably just tell you the surfaces we want you to use to classify them. So we took this question and just made it multiple choice, right? You have 8 possible options. They are the 6 quadratic surfaces plus cylinders plus a plane. So when you get to this type of question on the exam, there will be a word bank to choose from. So maybe you count that multiple choice. If so, it's probably the only multiple choice question we'll have that semester long on an exam. But I digress. I want to classify some surfaces. So let's do that. First thing I want to do is a brief exercise. In your head, I want you to picture the graph of y equals 4x squared. Right? Hold that in your head. Right? Hopefully you've got a parabola, just in case you're feeling lazy. That's the shape I'd expect you to have, roughly, right? Just a parabola, it opens up. Now, think about the graph of y equals 17x squared. I'm willing to bet that for almost all of you, the image that you had in your head didn't change between those two parabolas, right? Because you aren't focusing on the number that's out in front. You're thinking about the structure of a parabola. You're thinking about just y equals x squared. For the most part, I bet, again, that's what everybody thought of. My argument there is that the numbers really don't matter. When you get to this problem where you've got to classify surfaces, I think you should ignore all of the numbers. Just pretend they're all 1, 0, or negative 1. Because I think if I said, think about the graph of y equals negative x squared, I do think your mental image would probably change then. If you've got y equals negative x squared in your head, it's going to go down instead of up. So the negative is going to matter, but the number itself doesn't. So if I come back to each of these problems, I am going to just get rid of a whole bunch of these numbers. I'm going to save the constants for now. I'll deal with them in a minute. But I don't really want to focus on those at all. So again, I don't think they're going to be helpful. So I'll just rewrite each of these equations to be easier. X squared plus y squared plus z squared equals 1. X squared plus y squared minus z squared equals 1. Negative z squared minus y squared equals x. Negative z squared minus x squared equals y squared. Negative z squared minus y squared equals z. Negative x squared minus y squared plus z squared equals 1. So I don't really need to think of it as 3, but the constants usually aren't too bad. Z squared plus 1 equals y plus x squared. And 1 minus y plus x equals z. All right, so that's my first thought on this problem. So just ignore every single number. Then I'll go through and classify the easy ones, and then rewrite the ones that I think need a little bit of extra work. This first one, that's a sphere, right? All 3 square terms are positive, so it's a sphere, or an ellipsoid. But I'm pretty sure that the multiple choice option has like sphere / ellipsoid. We won't be picky between the two. If you say sphere when it's ellipsoid, you'll still get credit for that. Next easiest on here, the one right below it. I see a linear term with a couple of square terms. So that's a paraboloid. And the signs on my 2 square terms match. So it's elliptic. Compared to the one that's a couple below it. Wait, where did I put the other one? Yeah, the one that's a few terms below it. Where again, I've got a linear term with two square terms. But now that one, if I rearrange the equation, it's z squared minus x squared plus 1. So while it's still a paraboloid, this one's hyperbolic. While I'm down here, the one over to the right, that one's pretty easy. All my terms are linear, so it's a plane. Above the one I was working on a moment ago, negative z squared minus y squared equals z. I've only got two variables out of my three potential options. Anytime I'm missing one of my variables, I have a cylinder. Cylinder. Don't even need to think harder than that. We'll just call it a cylinder. So that leaves just three others. And three shapes I haven't talked about at all yet. Well, one of those has three square terms with no constant term. So it's pretty easily identifiable as a cone, which means the last two I've saved are the hard ones. I've got the two types of hyperboloids. Hyperboloid of one sheet versus a hyperboloid of two sheets. So I'm just going to rearrange my terms to make it a little easier to identify. All right, so I'm going to rewrite them so that I've got two positive square terms on one side and a positive square term on the other side. And then I'll move my constant to be with the solo term. Because I think that's the easiest way to distinguish between the two hyperboloids. Because both of these are my hyperboloids. Hyperboloid. This one's also a stop at. Hyperboloid. So I just need to determine the number of sheets. And if I rearrange them this way, if I've got a positive constant term, that's going to be just one sheet. Because they'll connect in the center, because I'll actually be able to get the equation of a circle near the origin. But if that constant term is negative, it'll be two sheets. Let's use blue again. Two sheets. Because I won't be able to get a circle near the origin. Cool, and then that's that problem. All right, and let's keep going with the last page. If you're joining for the next class, fortunately, you're also in Calc 3, so that works out great. I didn't quite finish the exam review during my lecture, so I'm going to take 10 minutes to finish the last page right here. I don't know if Nick will finish all of it too in his class, but just in case, here's the final page. Again, I ran out of time. So I want to find the arc length of a curve. If I want arc length, I'm going to come up to my formula sheets, which I conveniently have on the page. Oh, cool. My pen died. And look for arc length somewhere. Hey, look, there it is. It's on the top. Got it on screen at least. I'll go to fix something. But if I'm after arc length, I need to integrate the magnitude of the derivative of my vector function. All right, so make sure that you take a magnitude when you're doing arc length. But since I've got that formula right there, I'll just transpose it down to the problem that I care about, which is going to be, again, the integral from A to B of magnitude r prime of t dt, which in our case is going to look like something. Let me grab this and move it down, because first I'm going to need r prime itself. And for this problem, r prime looks like -3 sine of 3t, 4, and 3 cosine of 3t. There we go. All right, so that's my derivative vector. Again, I'm going to want a magnitude of that. A magnitude of r prime. And it looks like it's going to be the square root of 9 cosine squared of 3t plus 16 plus 9. Well, I mean, it wasn't wrong to say cosine squared, but I was trying to follow the pattern above. So it probably should have been 9 sine squared of 3t plus 16 plus 9 cosine squared of 3t. And then I think that simplifies rather nicely. Yeah, I'm not going to try extending that. So sine squared plus cosine squared is 1. Means 9 cosine squared plus 9 cosine squared is 9. 9 plus 16 is 25. The square root of 25 is 5. So this ends up being the integral of 5 dt from 4 to 7, which is going to be 5 times 3, or 15. Maybe I can expand that slightly. 5 times 7 minus 4, which is 15. 7 minus 4. Slide it a little bit over. Cool. So 15 is the answer I got there. Not too bad. And finally, one last problem. A little bit more challenging, but I think if you came up with a solution to this problem, you're in very good. You're in a very good position for the exam. So, okay, I've still got like 2 more minutes. Let's talk about this one. So I've got a vector crossed with some unknown vector, and it's equal to something that's given. And we're told that this equation has no solution, and we need to explain why. So, thinking about stuff we know about cross products, right? Anytime I take the cross product of 2 vectors, I should get a result that is perpendicular to both vectors. I can't really say much about v because it's supposed to be my solution vector thing I'm sort of going to solve for, but I do have 2 known vectors. And I know that for this cross product to be true, those vectors need to be perpendicular. So vectors must be perpendicular to their cross products. So if I could just show that those 2 vectors are not perpendicular, I'd have provided enough to have a solution, or I'd provide enough justification to say there's no solution. So easiest way to check if 2 things are perpendicular, really to just take their dot product, right? If 2 things are perpendicular, the angle between them should be 90 degrees or pi over 2 radians, which means the dot product should be 0. So let's try that. 1, 1, -3, dotted with -1, -1, 5, 2, which looks like -1 plus 5 minus 6. And what is that? 5 minus 6 is -1. And then -1 minus 1 is -2. So if I've done my math right, this is not 0. At which point I've shown those 2 vectors aren't perpendicular, so there should be no solution to the equation above. And one final thing, if you're looking for even more review, you can check the exam review section of my notes. There's a thing called the Exam 1 review. It's right there. And you can even find a video to that old exam review if you go to my notes and click on videos from fall semester 2025. Look in the Exam 1 content. There's an old review video there. And I am so over on time, so I'm going to get out of here. Okay, bye, 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 bye.